Let's start. TRAPPIST, the dark hot Jupiter. TRAPPIST is famous for reflecting almost no visible light. It's a scorching gas giant, but instead of bright, reflective clouds, its atmosphere seems to swallow starlight so efficiently that it's been described as one of the darkest known exoplanets. One explanation is that the intense heat destroys or prevents shiny cloud layers, while strong optical absorbers dominate, making the planet look more like black velvet with a faint thermal glow. Kelt 9b, hotter than some stars. Kelt 9b is an ultra-hot Jupiter with temperatures high enough that many molecules can't survive intact, breaking into atoms on the day side. At those extremes, metals can exist as vapor in the atmosphere, and the planet is blasted by fierce radiation from its very hot host star. It's basically a planet-shaped blast furnace, and it's expected to be losing atmospheric gas over time under that relentless heating. Kepler-36b and Kepler-36c, neighbors with totally different bodies. These two planets orbit the same star with orbital distances that differ by only about 10%, yet their densities are dramatically different. Kepler-36b is much denser and more rocky world-like, while Kepler-36c is puffier, closer to a mini Neptune with a thicker envelope. Same neighborhood, totally different build quality. It's a strong clue that migration, atmospheric loss, and early system chaos can turn near-identical starting points into wildly different outcomes. Kepler-16b, a real two-sun planet. Kepler-16b is a circumbinary planet. It orbits two stars that orbit each other. From the planet's view, you'd get a double sun that shifts position as the stars circle their shared center, while the planet loops around both on a wider path. Kepler detected it through transits, and it's one of the cleanest proofs that planets can form and remain stable, even in the gravitational weirdness of binary star systems. The PSR B1257+12 planets, worlds around a dead star. PSR B1257+12 is a millisecond pulsar, a neutron star that spins fast and emits extremely regular pulses. Tiny shifts in the timing of those pulses revealed planet mass companions, making this the first confirmed exoplanet system announced in 1992. It's still one of the strangest places to have planets, because the host is the leftover core of a star that already died violently. Whether these worlds survived, reformed from debris, or followed some other path, pulsar planets prove planet building is more stubborn than common sense. WSP-12b getting stretched and stripped. WSP-12b orbits so close to its star that tidal forces distort it into an egg-like shape, and there's evidence its atmosphere is escaping. Observations show an extended envelope of gas around the planet, consistent with a world that's basically overflowing and shedding material into space. On top of that, multiple studies have discussed orbital decay, suggesting it may be slowly spiraling inward over time. This is a hot Jupiter that's not just hot, it's physically being dismantled. WSP-193b, cotton candy density. WSP-193b is huge for its mass, roughly Jupiter-sized but with an extremely low density, often compared to cotton candy. It forces the obvious question, how do you inflate an atmosphere that much without it escaping into space? That's why astronomers get excited about planets like this. If the atmosphere is truly that puff, it should be a great target for transmission spectroscopy, unless high hazes or clouds hide the signal. Kepler-51d, a superpuff with a mystery atmosphere. Kepler-51d is another extreme superpuff, with a huge radius for a relatively small mass. JWST transmission spectroscopy suggests the planet's spectrum can be explained by high-altitude hazes that scatter light and flatten the usual absorption features. But there's a twist. Some interpretations showed the same data could also fit a tilted ring system that makes the planet look larger during transit. Either way, it's a great reminder that radius can be deceptive when haze, clouds, or rings get involved. TOI-849b, the exposed core. TOI-849b is roughly Neptune-sized, but unusually dense for something that big. That points to the exposed core idea. It may be the stripped interior of a planet that once had a much thicker gaseous envelope, but lost most of it to stellar radiation or violent past events. It also sits in the so-called Neptunian desert, where close-in Neptune-like planets are rare, which makes it even more informative as a clue to how atmospheres get erased. 55 Cancri E, a lava world that might still have air. 55 Cancri E is a super hot rocky planet on an ultra-short orbit, less than a day. It's often described as a lava world because temperatures are high enough to keep rock molten on the day side. JWST observations have fueled debate about whether it has an atmosphere, potentially replenished by outgassing from a magma ocean. Even if interpretations evolve as data improves, the headline is real. We're finally starting to probe atmospheric chemistry on rocky exoplanets, not just giant gas planets. K2-141b, rock vapor, winds, and rock rain. K2 to 141b takes the lava world concept and turns it into a full planetary weather cycle made of minerals. Models suggest a molten dayside hot enough to vaporize rock, creating a thin, rock vapor atmosphere. Winds transport that vapor toward the night side, where it cools, condenses, and falls as rocky rain or snow, then flows back as molten rock. It's basically the water cycle, but the water is stone. HD1 89733b, blue, windy, and full of silicates. HD1 89733b is known for its deep blue color in some observations, likely caused by haze and scattering, not oceans. It's also the planet behind the famous glass rain story, silicate particles forming high in the atmosphere and being whipped sideways by extreme winds. Whether you take the phrase literally or as vivid shorthand, the real point is that hot Jupiter weather can involve aerosols made of minerals, not water, with wind speeds that would erase anything remotely Earth-like. HR 8799e, a planet we can actually see and dissect with spectra. HR 8799 is a young system where multiple giant planets have been directly imaged, and HR 8799e is one of the best targets. JWST observations have detected molecules like carbon dioxide and carbon monoxide in its atmosphere, giving real constraints on composition and formation. Direct imaging is brutally hard because you're fighting the star's glare, but when it works, it feels like real planetary astronomy, collecting the planet's own photons and reading what they contain. TRAPPIST-1e, the compact habitability lab. TRAPPIST-1e isn't weird because it's extreme, but because the system is a perfect comparison experiment. TRAPPIST-1 has multiple Earth-sized rocky planets packed close together, and TRAPPIST-1e sits in the star's habitable zone range. That lets astronomers compare several similar worlds under the same star and ask, who keeps an atmosphere, who loses it, and why? Even no atmosphere detected is valuable here because it teaches us what small stars do to small planets. J1407b, the super ring mystery. In 2007, a young star called V1400 Centauri dimmed in a complex pattern for weeks. One explanation is that a companion object with a gigantic ring system passed in front, sometimes nicknamed a super Saturn. The object, often called J1407b, hasn't been cleanly confirmed, and later work argues it may not even be bound in a stable orbit, which would make it a one-time alignment event. But it's still an incredible lesson. Light curves alone can hint at rings, gaps, and maybe even moon formation long before you ever get a direct image. If you enjoyed this video, subscribe for more quick space explanations and hit like. It really helps the channel.